We said at the beginning of this unit that there were 4 properties of waves that are exhibited by EMR. One of them was diffraction, one of them was interference, one of them was polarization, and one of them is this topic that we've been doing for the last couple of days. It's called refraction. Refraction is the bending of light, or the bending of any wave for that matter. And it's due to the change in speed of a wave when it goes from one medium to another. As it changes speed, it also changes direction, and it also changes, what else? Speed, direction, and the wavelength. As the speed of the wave decreases, the angle will decrease, as will the wavelength decrease. Now, in order to really get this stuff and to mathematically deal with it, we had to define a new term called the index of refraction. The symbol for the index of refraction was n. Does anybody remember what the index of refraction was defined as? This is really important, this definition. Really important, because the definition leads us to an equation that's not on your data sheet. Yep? Okay. We'll write down the equation C over V, which really is a definition, right? Because the index of refraction is the ratio of the speed of light in a vacuum, which is C, 3 times 10 to the 8 meters per second, divided by V, which is whatever the speed is in that medium, which is always going to be lower than 3 times 10 to the 8 meters per second. Lower than or equal to 3.00 times 10 to the 8 meters per second. That makes n always what? N will always be, what kind of value are we going to get? It's positive, yeah, positive, but greater than 1. It'll always be, well, I shouldn't say always greater than 1. It could be greater than or equal to 1, right? So if you're dealing with air, let's say, where the speed of light is effectively 3 times 10 to the 8, then 3 divided by 3 is 1, and the index of refraction would be 1. That means that light wouldn't bend when it goes from a vacuum to air, at least not a particularly measurable amount. The speed of light in glass is about 2 times 10 to the 8 meters per second. So when we divide those two values, 3 divided by 2, we get 1.5. An index of refraction that's greater than 1. Light slows down more when it enters glass than it does when it enters air from a vacuum. Now, if we look at diamond, the index of refraction is 2.42. That means the speed of light in diamond is even lower than it is in glass. So we get a bigger change in speed, we get a bigger index of refraction, we get a bigger change in direction, we get a bigger change in wavelength. And ultimately, we'll learn this a little bit later on here, that's why diamonds sparkle so much, is because of all those properties that change as a result of this big index of refraction. Now, we also said that every material has a slightly different index of refraction for each different frequency or for each different color. And that results in a phenomenon called dispersion. When white light, or we'll draw it as yellow light here, but in the end it's technically called white light. When white light strikes this prism at this angle, then all of the colors of white light, which consists of red, orange, yellow, green, blue, indigo, and violet, they all refract. But because of the different index of refraction, they all refract a slightly different amount. Which one refracts the least? Red. Hey, which one refracts the most? Violet. So we're going to draw this where red is refracting a little bit and violet, blue, indigo, and violet are refracting the most. When we get to the other side, we get a similar phenomenon here. Ends up looking like this, of course, with all the other colors of the rainbow in between. This is the dark side of the moon, right? This is the Pink Floyd album. This is how we remember it, right? This is how we remember that small frequencies refract less, and therefore there is a smaller index of refraction for smaller frequencies. We remember that not by memorizing all those words, but by picturing that album cover that's up on the wall over there, picturing it so that we know that red light is bending the least. And then we can just kind of reason through the rest of it. Does that make sense? Okay, that's called dispersion. We also learned that that's what causes rainbows. Dispersion causes rainbows. And we also learned that the other day that that's what causes sunsets and sunrises to be reddish sometimes, and the sky to be blue in the middle of the day. Now, we ended off the day the other day on Wednesday with this equation, this new equation that we call Snell's law. Snell's law provides for us a relationship between the angle of incidence and angle of refraction. If this is the boundary, the solid line is the boundary between two materials, material 1 and material 2, then we would say that theta 1 right here, measured from the normal line, would be this angle right here in medium 1. Theta 2 would be this angle right here in the second medium as measured from the normal line. So this equation provides for us the relationship between those two angles. And it also provides for us the relationship between the speed and the wavelength and the index of refraction. Note the form of the equation, right? 1 over 2, 1 over 2, 1 over 2, and 2 over 1. That's the case because as speed goes up, as wavelength goes up, the angle goes up. But that happens because the index of refraction has gone down. Now, let's take a look at the drawing that I have up on the board here right now. You can see that theta did what? Decreased or increased? Theta increased. The angle got bigger. If the angle got bigger, that was a result of the speed doing what? Increasing or decreasing? Increasing. Okay, that also resulted in the wavelength of the light increasing. Ultimately, that was all because the index of refraction from medium 1 to medium 2 went down or decreased. Does that make sense? N went down. Okay, that caused V to go up, which caused theta to go up and lambda to go up. These three are all directly proportional to each other, and they're all inversely proportional to the index of refraction. You know, in this equation, you're only ever going to use two parts. How do you decide what two parts to use? Look at your givens, right? Like once you recognize that it's this kind of problem, a Snell's law problem, and then write down your givens, look at what you have, and see which two parts of the equation seem to work the best. So look at 3 questions on worksheet number 17 that we had for homework, specifically questions 5, 7, and 8. All right, number 5 says, light passes from air in a diamond, so we're going from medium 1 to medium 2 at an angle of 15 degrees. What's the angle at which the light leaves the air diamond boundary? I'm going to draw this out. I think in these questions it's useful to draw it out just to visualize what's going on with the angles and which material is index 1 and which material is index 2 and so on. We're going to make this our air, and we're going to make this one our diamond. Air has an index refraction of 1.00, and diamond has an index refraction of 2.42. And you're not going to remember those values necessarily, but you can get them somewhere. On your data sheet, it only has the index refraction for air, but if you need the index refraction for diamond on a test, you'll be given that somewhere within the question. All right. Passes in at an angle of 15 degrees. So let's draw that in and let's label that 15 degrees right there. At what angle does it leave the boundary at? Let's draw that refracted angle and try to draw it roughly to scale here. Is theta going to increase or decrease? In other words, we're going to get a value for theta that's bigger or smaller than 15 degrees?
Bigger.
Why do you say bigger? Okay. Well, you guessed wrong. Danny?
It's just my answer is smaller.
Okay. So you're saying smaller because you got that as an answer. Kyle, you said smaller. Yeah. As you go up in index of refraction increases, then the speed, the angle, and the wavelength will all decrease. So we're going to get something like this. Now, exactly what that angle is without calculating it, we don't know, but we do know that it's going to be smaller than 15 degrees. Probably quite a bit smaller because the index of refraction for diamond is so high. All right, so we're going to say sine theta 1 over sine theta 2 equals n2 over n1. There are 2 other parts to the equation, but we're not going to use those 2 other parts clearly because these fit the givens the best, right? All right. We're looking for theta 2. Sine 15 degrees over sine theta 2 equals n2, which is 2.42 over 1.00. I like it when we have air as our first medium because it always means that 1 is the denominator on the right-hand side, right? Just makes the math a little bit easier for us. Now we want to find theta 2, so we're going to take sine theta 2 up by multiplying, and then the 2.242 down by dividing. It becomes sine 15 degrees over 2.42 equals sine theta 2. Where did the 1 go? Well, technically it went up by multiplying, but it's 1, so it really just disappears. Let's take the inverse sine of this number on the left-hand side. When we do that, we get theta 2 is equal to 6.14 degrees. Does that seem like a reasonable number? Yeah, it's useful to make that prediction whether theta is going to go up or down, like we did when we started this question, right? We said that the index goes up, theta is going to go down. It's useful to make that prediction so that when you get an answer, you can tell right away if it's a reasonable answer. Okay, this sounds bang on to me because we knew it was going to go down because the index of diamond is so high, it was probably going to go down quite a bit, and it did. All right, let's take a look at number 7 now. Determine the ratio of the speed of light in a vacuum to the speed of light in ruby. Did anybody catch a lightning fast answer to this question? Did anybody think, oh wait, the answer is 1.54 right away? Right away. Yes, a couple of people did. Like, how'd you catch that? The index of refraction is defined as the ratio of the speed of light in a vacuum to the speed of light in that medium. That's what the index of refraction for ruby is defined as, right? So they're asking you, like they're giving you the definition, they're just asking for the value that's on the table. Now, you didn't recognize that? That's okay. Okay, we can find the ratio of the speed of light in a vacuum to the speed of light in ruby. Still another way. I'm going to say V1 over V2 equals N2 over N1. I'm going to say I'm going to say vacuum is 1, ruby is 2. That means we've got 1.00 over 1.54 equals N2 over 1.00. Make sense? Is that right? No, that's not right. V1 is 3 times 10 to the 8. V2 is, hold on for a second here. We don't know the speed of light in ruby, do we? Okay, so let's, if we know the ratio, the speed of light ratio 1 to 2 is the same as the inverse of the index refraction ratio, then let's just say N2 over N1. N2 is 1.54, and 1 is 1.00. So what I've done there is found the ratio. If the ratio of the indices of refraction is this, then that's the same as the inverse of the ratio of the speeds. So at least you don't have the speeds, then get the inverse of the ratio of the indices of refraction, because it's the same value, right? Now the other thing you could have done here is said, well, we know what V1 is. It's 3 times 10 to the 8. You could have found V2 using this, right? Knowing what N2 is, C is 3 times 10 to the 8, solve for V2, and then divide the 2. Guess what you would have gotten, right? Make sense? Either way works there. Okay, number 8 says determine the ratio of the speed of light in crown glass to the speed of light in quartz glass. We're going to do almost the same thing for this one. We'll say we're going from crown glass to quartz glass, although it doesn't really matter. We could go the other way around. It doesn't really matter. No, we wouldn't actually, because we're finding the ratio of crown to quartz, so it has to be crown over quartz. That's going to be equal to N2 over N1. So let's do exactly the same thing here. The index of refraction of quartz glass is 1.47. Crown glass is 1.52. This is the ratio of the index of refraction of quartz to crown, which is exactly the same as the ratio of the speed of crown to quartz. Okay, we do that, we get 0.967. This one we couldn't have just picked the index of refraction because our frame of reference was not a vacuum, right? In the first one here, question number 7, It was the definition of the index refraction of ruby. This one, number 8, is not the definition of the index refraction because our reference point isn't a vacuum.